Everyone, hope you guys are doing well. This video was recorded in like multiple parts. Sorry about that. I do talk a little bit slow, so please feel free to speed up the video. Please feel free to speed up the video to your liking. Um, Hope studying is going well. Good luck. Oh, wait, how do I? What's good with it? Today we're gonna be going over skill practice 6. Yeah, let's get right into it. So, skill practice 6, just 4 questions, right? You might think that like, oh, that's easy. Don't worry about it. But these are questions that are hard. These are long questions. So let's get right into it. How much energy is required to change the temperature from 210 grams of H2O from -40 degrees Celsius to 155 degrees Celsius? So right here, there's a couple things we can point out here, right? 210 grams. That's our mass. And then we have a temperature change from 40 degrees Celsius to 155, right? And what this tells us is that this goes, if we look back on 6.1, right? 41 degrees is like somewhere right here, and then 155 is somewhere up here, right? So when we go from -44 to, or yeah, -40 to 155, we go through a melting and also evaporation. So we go through two phase changes. Okay, oops. So you go through two phase changes, right? So we need to keep that in mind. You go from ice to water, and then from water to steam, right? And so in order to get in order to get ice into water, there's two things. Or yeah, well, let us list out the steps, right? So we are from -40, right? In order to get to a liquid form, because we're at a solid, from -40 to liquid, we need to melt it. But in order to melt it, we need to get to 0 degrees Celsius. So from -40, we need to go to 0 degrees Celsius. And then in order from go from liquid to water, right? When you go through melting stage. And melting is we just need to melt it. That's its own equation itself. And then so right now, in order to go from so right now we're at 0 degrees Celsius, right? And we need to get to 155. But at 100 degrees Celsius, there's evaporation. So when you go from 0 to 100. So from 0 to 100, that's a liquid state. And from the liquid state, it's just go from 0 to 100. And then once we hit 100 degrees, we need to evaporate it. So we need to evaporate. And then furthermore, right? After we evaporate it, we're still at 100 degrees Celsius. But we need to get to 155. So we need to go from 100 degrees to 155 degrees Celsius. So looking at these steps, right? You have to go through you have to go to 1, 2, 3, 4, 5. 5 steps. Yeah, let's do it on a separate piece of paper so I get more room. So for number 1, right, we have to go through all these steps and find out like the total. So for number 1, right, when you go from -40 to 0 degrees Celsius, and we need to find how much energy it takes to go from -40 to 0 degrees, we have to use Q equals MC delta T. Right? Q is our energy we need to find. M is mass. We know what our mass is. That's going to be 210. C, that's our specific heat and degrees and temperature change. So let's get right into it. So we need to find out what Q is, right? Our mass, right? Our mass is 210. Oops. The mass is gonna be 210. And then next, 210. And then look, we have to find out our C, our specific heat. And so to find out what our specific heat is, because there's a couple of them, we need to look at what we're dealing with already. We're working from -40 to 0 degrees. That's in our iced form. We're in a state of ice. So the specific heat of ice, uh, Mr. Lee will always give us this to you during your tests, but like it's good to know. I'll just tell you guys right now. Specific heat of ice is going to be 2.06. And there, our temperature change is just this, right? We go from like what is the temperature? What is the temperature change from -40 to 0? And that's going to be 40 degrees. And we know this because 0, we're subtracting from -40, or yeah, let me just do it like this. Oops. 0 minus -40 degrees Celsius. Because right, we have final minus initial. Our final is 0 degrees. Our initial is 40. Final minus initial. Negative, double negative turns to a plus. 0 plus 40 equals 40. So it's going to be 40 degrees. Q is going to be about 17,304 joules. And then I think so, right? Yeah, 210 times 2.06 times 40. Yeah, 17,304. Okay, that's our first step. And we'd have it done. This is number 1. So it's going to be Q equals 17,304. Now it's number 2, right? So for number 2, we have to melt. And the formula for melting is just going to be the mass times the melting, like whatever it takes to melt, like the constant to melt. And Mr. Lee will always give you this, so it's pretty easy. So it's going to be mass times like the H for melting. So mass is going to be 210. Our enthalpy is going to be 334. Hold on. Be right back. Okay, random tug. Okay, we're back at it. Okay, so right, we're at 210, right? We have our mass 210 times our enthalpy, which is going to be 33.4 334 joules per gram. If I'm not mistaken, yeah, joules per gram. And then we multiply this out, right? Because this is going to be our phase change from uh ice to water, from salt. It's going to be our melting change. It's going to give us 70,140. I think it's kind of thick. 7140, right? All right, cool. So this is gonna be so this over here, right? Your Q or this is yeah. Okay, number 3. So number 3, right? Looking over here, because look, we just did we did melting, right? So now we're on to number 3. So number 3 is gonna be raising the heat from 0 degrees Celsius to 100 degrees Celsius. Oops. Right, so whenever we're raising heat, we're gonna be using Q equals MC delta T, right? So Q equals MC delta T, right? Q, so that's gonna be what we're trying to find, right? How much energy it's gonna take. M, right? Same thing as it goes, 210. Specific heat, C, right? Up here, when we went from -40 to 0, mm, or we went from -40 to 0, right? I was from ice, right? And that's why we used 2.06. But now since we melted the ice, now we're in water. So we can't use 2.06 anymore. So the specific heat of water, right? Mr. Lee is going to give you this as well. It's going to be 4.18. And then for like the temperature change, right? We're going from 0 to 100, right? Final minus initial, right? Our hundreds are gonna be our final, 100 degrees Celsius are final, zeros are initial, give me 100 degrees, right? And then we multiply all this out, all right, plug and chug. This is going to give us about 87780, right? So cool. This is number 3. Okay, now we're on to number 4. Evaporate. So this is again another phase change. So we went into the phase change, right? It's still going to be the same like M times delta H type of thing again. M delta H, M enthalpy. Our mass is still 120 to 210. Right? This is not going to change. This is not going to change whatsoever. 210. Enthalpy is going to be for water, right? Because we went from water to gas to evaporate. The enthalpy for is going to be 2260 joules per gram. 2260. So you multiply this out, you're gonna get 474,600, right? Okay, cool. And then now, since you have all these values, right? Right, you have one. Right, you have one. You have one. Oops. You have 1, 2, 3, 4, 5. This is going to be your 1. Oops. It's going to be your 1. 1, 2, 3, 4. Oh, forgot one more thing. Right. Number 5. You have to raise it to 155 degrees Celsius. And this is going to be the same thing as the Q equals MC delta T, right? Because we're just raising temperature. Q is what we're trying to find. M, same thing as it always goes, 210 grams. C, now we changed the specific heat for water. Now it's going to be for steam. Specifically, the steam is going to be 2.02. Mystically will always give you this stuff, like all this like constants and stuff. And then the temperature change is going to be 55 degrees, right? Because we're going from 100 to 155. That temperature change is going to be 55 degrees. All right, so Q is going to be, if you multiply all this out, you're going to get 23,331. Right, so now as I was saying, you have all these, okay, so you can have 1, 2, 3, 4, and 5. And so you need to find the total amount of energy required. So what you do is you just add them all up together. All right, so it's going to be 17,304 plus 70,140 plus 87,780 plus 474,600 plus 23,331. And this, you guys, should give you a grand total of 673,155. Yeah, so it's gonna be 673,155 joules. All right, now on to number 2. Let's get into it. Yes, let me just copy this and paste this bad boy right here. This. All right, cool. Number 2. How much energy is required to heat up 45 grams of water at 55 degrees Celsius to 140 degrees Celsius? All right, yeah, sorry. One more thing. Notice how we went from all these stuff right here. Notice how like we went from Q equals MC delta T to mass times enthalpy back to Q equals MC delta T. So we always like alternate, right? Q equals MC delta T times mass times enthalpy, right? Because look, Q equals MC delta T is the first one. Then we go into mass times enthalpy, and then we go back to Q equals MC delta T, and then we go into mass times delta H, and then Q equals MC delta T. So we always like flip flop. We like alternate between them. All right, so next one. How much energy? Let me plug in my iPad. Okay, cool. How much energy is required to heat up 45 grams of water at 55 degrees Celsius to steam at 140 degrees Celsius? So, right, look, we're at 55 and we need to get to 140. And so back into the other slide, right? 6.1. It's right here, yeah, right here. 6.1. We're at 55 is like right here ish. And then 140 is all the way up here. So we need to go through, we're at water when you go to gas. So we're gonna have to evaporate the water. And since our water is not yet at 100 degrees Celsius, right? It's still at 55. We need to go through 3 steps, y'all. 3 steps. First step is going to be raise. We need to go from 50. We need to raise the temperature of the water from 55 degrees Celsius to 100 degrees Celsius. Our second step is going to be that phase change, as we said earlier. That's going to be 50. We're going to have to evaporate the water. And then the third one is going to be raising it from 100 degrees Celsius to 140, right? So three steps. We need to add them all 3 values together. Okay, right? So let me do this on another sheet of paper. Pull it down here. All right, cool. Cool. 55 degrees Celsius to 100 degrees Celsius. Okay, yeah, anyways, so we go from 55 degrees Celsius to 100. We need to raise it, right? 55 to 100. Yeah. So, all right, whenever we raise temperature, that's going to be Q equals MC delta T. So it's going to be Q for from Q equals MC delta T. Number 1. Q is what we're trying to find, right? Mass this time is going to be 45 grams. Let's put it down here. 45 grams. C is going to be right, water, the specific heat of water is going to be 4.18. And temperature change, right? Since we're going from 55 to 100, we need to subtract the final minus the initial, right? 100 minus 55. It's going to give you 45. So our temperature change is going to be 45. And then Q, you multiply all this out, you should get somewhere near 8,464.5. Right? That's number 1. Number 2, right? It's going to be mass times enthalpy. Mass is going to be 45, right? Enthalpy is going to be 2,260. Multiply this out, you're going to get 101,700. All right, and it's number 3. We still same thing as Q equals MC delta T. Q is going to be 2.02 times the mass is going to be 45. C is going to be 2.02. And then the temperature change is going to be 40. And the reason why it's 40 is because, look, we're going from 100 degrees Celsius to 140. So we have to raise it by 40 degrees. Okay. You multiply this out, you're going to get 113,800 joules. Oops. You add all this up together, right? Bam, bam, bam. Should get around, oops, sorry, I did this wrong. Oopsie daisy. That's kind of embarrassing. Okay. You multiply all this out, right? This part, you should get 3,630. And then finally, when you add up all these values, right? 2 and then 3, this one, you're gonna get 113,800 joules. Cool. The next one. Let me just cover this up. All right, what's up? So yeah, we're on to number 3. Consider a coffee cup, right? Has a temperature of 93 degrees Celsius Assume the mass of coffee is 550 grams and the specific heat of coffee is about the same as the specific heat of water. Is a 230 gram of ice cube at 0 degrees Celsius large enough ice cube to bring the temperature of the coffee cup to 23 degrees Celsius? Note the final temperature of the ice cube and the coffee is 23 degrees Celsius, right? So let's picture this out, right? So we have a coffee cup. Well, essentially we have an ice cube and we have a coffee cup. When you drop this, and this ice cube is kind of cold. It's very cold. It's at 0 degrees Celsius. And this coffee cup, right? This coffee cup is at 93 degrees Celsius. This is steaming hot. When we drop the cold ice into the boiling hot coffee cup, right? We're gonna see the temperature brought closer and closer. So the temperature of the ice cube of the coffee cup is at 93 degrees Celsius, right? It's up here. The ice cube's at 0 degrees Celsius. So when the 0 degrees Celsius is right here, when you drop the ice cube into the coffee cup, the ice cube's temperature is going to rise, and then the coffee cup temperature is going to lower until we hit about an equal temperature, and that equal temperature is going to be 23 degrees Celsius, right? So when the coffee cup lowered, right, then the initial was at 93, and the final was going to be 23. So that temperature change essentially is going to be 23 minus 90. And 23 minus 90 is going to be oh wait, hold on. 23 minus 93. My bad. Give me negative 70. Yeah. Negative 70. So for ice cube, let me write this out. For ice, the delta T is going to be negative 70. That's a temperature loss because it's negative because it lost heat. And then the mass of the coffee cup is going to be 550 grams. The mass is going to be 550. And the specific heat of a coffee is about the specific heat of water. The specific heat of water is going to be 4.18. Is a 230 gram ice cube at 0 degrees Celsius large enough ice cube to bring the temperature of a coffee cup to 22 degrees Celsius? So the ice cube, oh wait, hold on. I just did this all wrong. This is coffee. The ice, the temperature is at the initial is at 0 degrees Celsius. But at the end, it's going to be brought up. It's going to gain heat to 23 degrees Celsius. That temperature difference is going to be 23. That mass of the ice cube is 230. And the uh specific heat, the specific heat of water is going to be the specific heat of the ice is going to be so specific heat of the ice, right? Because it's already at 0 degrees Celsius, but we needed to take it to 23. And so there's going to be two phase changes here. We already know it's an ice, so we need to turn that into water. And to turn ice into water, we need to melt it. So that's we have to go through one phase change. That's melting. Second one is bringing the 0 degrees to 23, right? So the specific heat is good. The enthalpy, I should say, the delta H is going to be 334 grams per like joule or something. And then the specific heat, right? Because once we melt the ice, it's going to be at once you melt the ice, it's going to be in water. And the specific heat of water is going to be 4.18. So we have our two things right here. 1, 2. And so when the question essentially asks us, is this ice cube, going to exert enough energy? And is the coffee cup going to exert enough energy to is the ice cube going to exert enough energy to bring the coffee to 23 degrees Celsius, right? Because we're considering that the coffee cup is going to be brought down to 23 degrees Celsius. We need to one see how much energy does this ice cube release, and two, how much energy is a coffee cup going to how much energy is required, right? Or needed to take this coffee cup to 23. And then when we get these two different energies, we need to see does it match? Does it meet the requirements? And so when I said that like that Q has to equal the other Q, that's also known as Q system equals negative Q surroundings. This negative right here can be placed at the beginning or Q system or Q surroundings, doesn't matter. But we know that the coffee cup is going to lose heat, right? It's going to be the temperature is going to lower down, so it's going to lose heat. That's why the negative is on this side. And then so we first need to see, right, as I said before, is what we need is the energy that's good. How much energy is going to take to bring the coffee cup down to 23 degrees Celsius, right? That's our minimum, a minimum amount of energy. And then we need to see, does this ice cube at 550 grams at 0 degrees Celsius, is that energy, is it going to meet it? Is it going to meet the minimum? Okay, so let's look at what we need at least, the energy we need at least. And we need to look at the Q surroundings. Because we know that the surroundings, it goes from 93 to 23. We need to see like to bring the temperature down from 93 to 23. So we expand Q surroundings is going to be MC delta T. M is going to be 550. C is going to be 4.18. Our T is going to be negative 70. And then we multiply all this out. You're going to get around 550 times. Should get 160,930. Right? So this is the minimum amount. This is the energy needed. It's required to bring this coffee cup down to 23 degrees Celsius. It's the amount of energy required. And now we need to see how much energy is this ice cube going to exert. And is this exertion, is the amount of energy going to be exerted? Is it going to reach 160,000? So let's find that out right now for Q system. Q system is also MC delta T, but we're looking at the system. So the system is going to be the ice, the mass of the ice cube, or the mass of the ice, right? It's going to be 230. And the specific heat of the ice. Oh, hold on. I need to do one thing. Try to do one thing here. I'll explain this. So we're in the ice stage right now. But when we bring it up to 23 degrees Celsius, we're going to be in water. It's going to be water already. So what we need to do is melt this ice. Sorry. What we need to do is melt this ice and then raise it to 23 degrees Celsius. So we're going through one phase change and then one like elevation. So the ice, right? In order to melt it, that's the molar heat of fusion. Our mass is going to be 230. 230. Our specific heat is going to be 334. 334, right? We multiply both of these together, 230 times 334. We're gonna get 76,800. Um, 76,820. And then for the Q equals MC delta T, right? We're at 0 degrees Celsius. We need to raise it to 23. Our M mass is going to be MC delta T. Mass is going to be 230. C specific heat is going to be 4.18, right? Because we're in the liquid phase. And then the T, the temperature change is going to be 23. So we multiply this out together, 230 times 4.18 times 23. You're going to get 22,112, 102.2. And then to find the Q total, the amount of heat totally release is going to be, we just add both of them together. This one, 76,820 plus 22,112. And we get 98,932. And so we see, right? This number, 160,000, is the energy need. It's the energy at least to bring, like, theoretically, the amount of energy released to bring this 93 degrees Celsius coffee to 23 degrees Celsius. And then this number right here, 98,000, is the actual energy that's going to take it from 92 degrees Celsius to whatever. And clearly, we see the 98,000 is way smaller than 160,000. So it doesn't even meet the minimum. And so what this means is that the ice cube, it's too small because it's not big enough to reach 160,000. Because as we said, look, we found out it only expended enough 90,000, but we needed a 160,000. So we need to say, no, not big enough. All right. Hope that helps. All right, number 4. Consider a pot of water at 100 degrees Celsius. If it took 1,048,815 joules of energy to vaporize the water and heat it to 135 degrees Celsius, how many grams of water were in the pot? Okay, so we need it. Okay, so basically, we have the pot is at 100 degrees Celsius, and it's theoretically it's at 100 degrees Celsius right now, and we need to bring it to 135. And from bringing it from 100 to 135, this took 1 million joules of energy. It took that much joules of energy to bring it from 100 to 135. And so what we need to find out is how many grams. So we found the temperature. We know the specific heat because it's water and steam. But we need to find out the M, mass. That's what we don't know. So there's 2 things here we need to do. There's, in order to find out the Q total, there's one phase change, right? And that's to vaporize the water. And then from 100 to 135, that temperature difference, how much energy is it going to be needed to raise the temperature of water to 135, right? So we need 2 steps. 1, vaporize. 2, raise from 100 degrees Celsius to 135. And we know vaporizing and Sorry, what did I say? We know vaporizing and raising the temperature, those two things is going to equal 1,040,815. Right? We know it's going to take that much energy. So vaporizing, so what it's saying basically, if I write this out, is going to be the vaporization to vaporize plus raising raising 100 to 135 is going to equal 1,048,815. So vaporizing is mass times enthalpy to heat diffusion. Since it's at water, the Michelin is always going to give you this too, but it's going to be 2260. That's going to be the enthalpy, the molar heat of the enthalpy to to vaporize. So to be mass times 2260, because you don't know the mass, we're trying to find out the mass. Plus to raise from 100 to 135, that's going to be another Q equals MC delta T, right? Our M, we don't know. Our C is going to be, we're going to be already at steam. So the specific heat of steam is going to be 2.02. And I know this because I'm also looking at my past assignment, but it's going to be given. Our T is going to be the temperature difference from 100 to 135. That's going to be 35 degrees Celsius. 1,048,815. All right. So basically, we just need to find out what M is. We need to isolate M. So if you factorize M out, you're gonna get 2260 plus this times that, so it's 2.02 times 35, 70.7 is 1,048,815. That added together, 2260 plus 70.7 is gonna be M equals, oh, it's gonna be 23,330.7. Let's bring this down. Oops. Right? And then what we need to do to isolate this M is to divide 23,330.7 on both sides. Divide by 23,330. No, 2,330.7 divided by 2,330.7. And our M is going to be, let me change colors. It's going to be 1,048,815 divided by this 450. Our mass is 450 grams of H2O. Sweet. And this, you guys, this is skill practice 6. Thank you.